Yeah, thank you for that lovely introduction, for the invitation, Nicholas and Jessica. I'm really sort of delighted to be here, to be able to speak with you all. This is the first set of in-person talks I'm giving since the pandemic, so I thought what a great opportunity to put something new together. And being in, this room with all of you all, being at the HCIL, one of the oldest, most prominent HCI labs, I thought that I would use this talk as an opportunity to sort of work out my own thoughts about what the role of HCI should be in the face of, well, this, right? The rapid progress that seems to be happening in AI, and particularly around LLMs, especially in the last 6 months. And for myself, at least, when I find myself in moments where there seems like a lot of overwhelming things happening, I personally like to slow down, and I'm very much a student of history. And I really like this chart from Jonathan Gruden, who wrote this 2009 article in AAAI about how AI and HCI are two fields divided by a common focus. And as you can see, sort of, when there are peaks in AI, there are troughs in HCI and vice versa. And so there's maybe a concern I initially feel that the rapid progress that AI is making maybe swings the pendulum back in the direction of ever more increased automation at the expense of, say, HCI-esque approaches of intelligence amplification or augmentation, like the title of my talk. So, for instance, if we cast back to the very first AI winter there, not only with Ivan Sutherland's Sketchpad, but, where HCI was often thought of as being birthed by, this paper by Licklider titled Man-Computer Symbiosis. And I think it's unfortunate gendering and unfortunately reflective of the time, but in the paper, Licklider sort of describes, here we go, I need a better clicker, a process in which problems would be easier and faster to solve if they could be done so through an intuitive guided trial and error procedure in which the computer cooperated, turning up flaws in the reasoning or revealing unexpected turns in the solution. And here is a demo from OpenAI where, GPT-4 is now sort of cooperating with someone to do some data analysis. So I upload a music.csv file, and then I can pose natural language expressions to say, how many rows does it have? How many columns are in the in the data set? And can you run some basic visualizations for me? And, I don't even have to stare at that demo very hard to feel like, have we achieved Licklider's, vision to think in interaction with a computer in the same way you think with a colleague whose competence supplements our own? Like, is it time to roll out our mission accomplished banners? And I'm not so sure. So a couple years after Licklider, Douglas Engelbart published what I think is just a foundational piece on augmenting human intellect. And right in the introduction, we start to see differences in how Engelbart sort of expands Licklider's vision. So it's no longer just on sort of deriving solutions to problems, though that's certainly a part of it. But what Engelbart is imagining is how computers can help us think, right? Increasing our capability to approach a complex problem situation, to gain comprehension about the problem. It's not just about solving problems, but deeply understanding them. And in particular, the way Engelbart is imagining a lot of this happening, of course, is with our sort of human intuition, our feel for sorts of things, but that coexists in particular with streamlined terminology and notation. And I think that's a particular key feature that I'm going to kind of continue to return to in my talk. So I wanted to sort of contrast that ChatGPT style interaction that we just saw with a system called B2 that I worked on with colleagues at Berkeley, in particular, Yifan Wu and Joe Hellerstein. And what B2 is trying to do is think about how you take a data science environment like a Jupyter notebook that is all about sort of programmatic data analysis and incorporate elements of interactive visual analysis that we might be more familiar with in, say, a tool like Tableau. So I could import B2 and start to use a library like Pandas or any kind of data frame package to do the same sort of how many rows, how many columns are in the data set. And when I invoke B2, what you'll see on the right-hand side is actually something that resembles, a graphical user interface that lists out, the fields in my data set. And what I can start to do is programmatically, do some data analysis and produce visualizations. But there's a couple of interesting things happening here. First of all, in that fourth cell to the left, I've automatically generated a visualization via B2. I've not had to manually specify I want a bar chart. This is what I want on the X or Y axis. B2 has automatically inferred, the appropriate specification for the visualization and produced it out. And the way it's done that is by analyzing the data frame and analyzing, the transformations I've made to it. Similarly, when I clicked on one of the cells on the right-hand side to produce the equivalent visualization, not only was the visualization produced, but code for that visualization was also produced that I was then able to go in and edit, to sort things or things like that. And then I can sort of continue through this analysis process in a really interesting fashion. So whereas with a lot of visualizations that we find in Jupyter notebooks, they remain pretty static, the visualizations in B2 are interactive, and as I interact with them, you'll notice that it's producing this interaction history as code in the cells. And in particular, if you pay close attention to what that code is expressing, it's expressing not mouse clicks and keystrokes and these low-level, interactive operations. It's expressing things that I, as a data analyst, would care about. So here are the states that I've selected. Here are the years that I've selected. And in particular, it's keeping a whole log of that interaction history. So I can go back in time and say, oh, you know what? Let me reproduce some of my interactive analyses to see, if I can recall what it is that I was doing. So I can just, comment and uncomment things out, even reuse part of an interactive result in a future cell, things like that. So there's a very tight integration between the input that I'm using, which is, programmatic code, the output that I'm producing, visualization, and then using the visualizations to further produce, code and conduct my analysis. Now, to me, at least, and maybe this is just me with my rose-tinted glasses because this is my work, yada, yada, I put these two things side by side and I go, boy, they feel really similar at some level, right? There's still that sort of back and forth conversational feel. Sure, on the left-hand side, it was a natural language conversation. On the right-hand side, it was programmatic. But how could I more deeply understand whether ChatGPT was doing something new or not? And what I realized as I was thinking about this more, I wish Ben S. was in the room. Oh, he's on Zoom. Fantastic. Hello, Ben. What I realized was that direct manipulation still matters, right? And so direct manipulation, of course, is the term that Ben defined in the 1970s. And when Ben was thinking about this, I think it started with a focus on the graphical user interface, right? So issues of having physical representations, buttons, continuous representations, undo, redo, things like that. In the 1980s, cognitive scientists Edge Hutchins, Jim Holland, who was my undergrad advisor, and Don Norman took Ben's work and expanded it to think about, how cognitive science allows us to think about direct manipulation, not just in terms of graphical user interfaces, but interfaces more generally. And in particular, what Hutchins et al. Did was identify, these two poles of user goals and the user interface. And they mapped out sort of this gulf of execution that we need to cross when we have to figure out how to translate our user goals into operations in the interface. And then a commensurate gulf of evaluation to figure out, whether the interface has done the thing that we've wanted to do. And the gulf of execution and evaluation, they're pretty familiar concepts, I think, to a lot of folks in HCI and user experience. They're often, things that we think through. But in that paper, in that 1985 paper from Hutchins et al., they actually go one level deeper that I really, really like. In particular, for each of these gulfs, they identify two types of distances. The first is a semantic distance that is trying to capture the meaning of what it is that a user wants to do, right? What is possible to say in the interface language, whether that is a graphical user interface, a textual interface, a conversational interface, what have you. And as you cross that semantic distance, you're basically taking that fuzzy conceptual model that you have in your head and figuring out how to translate that conceptual model into the nouns and verbs of the user interface, right? So how do you start to form an intention, and how do you start to maybe specify what those actions might be? In addition to a semantic distance, they identified that an articulatory distance exists as well. So this is not about the meaning of what I'm saying, but rather how I express that meaning to the system, right? So just like we saw with B2, I could have both a textual representation and a visual representation that are expressing the same meanings, right? The same semantics. But because I'm using text in one case and vision in another, the mechanism by which, the form by which I'm expressing those semantics is very, very different. And of course, those same distances occur across the gulf of evaluation as well. So once the user interface is in some particular state, there's an articulatory distance that I have to cross through my perceptual senses. And then I begin the interpretive process to figure out whether I'd actually achieve my goals, right? And it's that interpretive process that is doing the sense making, right? Is bringing back meaning, translating back from the nouns and verbs of the user interface, again, graphical, textual, what have you, into the conceptual model that I have in my head. So this is roughly the machinery, the outline of the rest of the talk. It is a little bit complex and dense. And so what I want to do is just return to these two examples and think about how they demonstrate semantic and articulatory distance. So if we start by considering semantic distance with ChatGPT, I would argue that there's not actually a very explicit set of semantics, right? It's a learned latent space, which means that the semantics are very implicit. It's hard for me to know what the nouns and verbs are that I can tell ChatGPT to do, right? But these large language models are pretty incredible in how they're actually able to very rapidly, almost zero shot, learn those semantics. And that's why we have prompt engineering, right? But prompt engineering, at least as it stands right now, to me, feels a lot like alchemy. Like we don't really know what it is we're doing. We don't know how to be systematic about it. There's a lot of sort of tips and tricks of the trade and sort of backroom, Twitter conversations about, oh yeah, if you tell it, like, think of yourself as, an engineer, et cetera, et cetera. And so what that means is it's very hard to be predictable, to be consistent, and perhaps most importantly, to be reproducible in the sort of work that you're doing. On the other hand, with B2, we had an explicitly defined set of semantics, right? They were domain-specific semantics related to visualization and data analysis. We had the semantics of pandas. We had the semantics of Altair and Vega Lite, which is a visualization library. And most importantly, that model was shared between not only the data analyst who was sitting there typing out the code, but was the same conceptual model that the system used, which is why when I clicked, a button on the user interface, it produced code in the same, terms that the analyst was thinking about. Now, the articulatory distance is often what a lot of us focus on when we come to analyzing user interfaces, right? So the big, huge advantage of these large language models is that I don't need to learn some, gnarly idiosyncratic programming syntax. I can express things naturally. So if I don't know exactly what my goal is or how to express that, that's fine. I just express something ambiguous and then back and forth, like Licklider's vision, figure it out with the model. But in the case of something like data analysis is often performed by sort of expert users, and they don't need to always be expressing that ambiguity, right? There's often, we know exactly what it is we want. And wouldn't it be nice to just be able to precisely say, not I want basic visualizations, I want exactly this visualization. And it's really, at least right now, quite hard to do that with a large language model. And as a result, there ends up being this disconnect between the input notation and the output notation. So I'm not able to take some output that the large language model produces, feed it back in directly to it and say, let's keep working with it, right? Let me brush on the visualization, do some analysis with it, so on and so forth. Again, I don't know that that's a fundamental limitation, but it's certainly a limitation we have right now. On the other hand, with B2, programmatic syntax, we all know the pros and cons of programming languages, I think, right? So a learning curve, but much more precise specification, but it gives you that shared form, right? That shared articulation, the shared expression that allows there to be kind of consistent semantics and integration between input and output. So that is just those two user interfaces all together. But I wanted to sort of dive into where that ChatGPT demo left us off with, which is, it produced these basic visualizations, and then it produced this, I don't know, explanation, description, something, right? It said, here's some basic visualizations based on the music.csv data set. Number one, a histogram of song durations, this shows the distribution of song durations in seconds. Number two, scatter plot of song hotness versus artist familiarity. This shows the relationship between song hotness and artist familiarity. Those are not terribly useful descriptions, but they demonstrate a promise, at least, that a lot of people are attending to about the opportunity to use these large language models to make visualizations more accessible. And so a lot of, particularly the big tech companies have deployed, whether it's large language models or other machine learning models, to do things like automatic image descriptions and things like that. And a lot of people have studied the effectiveness of these automated opportunities to do description. And here are some of the things that blind people and people with low vision tell us about how effective these things are, right? So the reader doesn't get any insight from texts like these, which not only increases the reading burden, but also conveys no effective information about the data. Another blind participant in interviews we conducted said that, the reading, the textual description is doing all of the interpretive part of the work. It's getting you all the way across the gulf of evaluation, but I want to be able to control how I consume the data. I want to have the time and space to interpret the numbers for myself before, doing any interpretation. And you don't have to squint very hard at these, these findings to realize that they actually map to those notions of semantic and articulatory distance, right? On the left-hand side, not getting any insight, that's a semantic problem. There's not very much important meaning being conveyed in these descriptions. And giving people time and space is about the form that these textual descriptions are conveyed. And so I want to start by focusing on the articulatory distance and how we might address that. But before I get into that, here is just a quick demonstration from my student, Jonathan Zhang, who led a lot of this work, on how people who are blind or low vision, what assistive technology they use, in particular called a screen reader, to experience.
If you're not familiar with how screen readers work, there's essentially a cursor, which will be represented here in a second visually using a black outline. And the user can use keyboard shortcuts to move this cursor around the page, and whatever's selected by the cursor will be read out as text-to-speech. So here I can demonstrate what the accessible HTML version of our paper looks like to a screen reader.
Visit link heading level 1. Hi, we're the MIT visualization group. Visit link home middle dot link middle dot link heading level 1, which screen reader experiences for accessible data visualization. Link best paper honorable mention article. You are currently on an article inside of web content. Heading level 2 items. Abstract. Current web accessibility guidelines ask visualization designers to support screen readers via basic non-visual.
Great. So as you can see, what a screen reader does is it takes the output that is conveyed on the screen and narrates it out, right? And the core challenge here, particularly in the visualization context, is that narration is unfolding linearly, right? So how do you take this artifact that one would otherwise previously think of as inherently visual, right? All of us, I think, probably read visualizations in myriad diverse ways. Maybe someone starts with a title, other people start with the axes, or you just look at the trend, etc. How do you linearize the process of reading a visualization while still preserving, the rich affordances of the medium at being able to get data at different levels of fidelity and things like that? So what Jonathan and two of the other PhD students in my group, Crystal Lee and Ellen Lundgaard, developed is this hierarchical structure of representing the data and the visualization textually. And in particular, what you'll notice with this hierarchical structure is it sort of preserves the sort of information-seeking mantra that Ben developed decades ago, sort of providing an overview of the data first. So you've got at the chart root some sort of summary description, a scatter plot with X and Y axes and these sort of categories. And then you can start to dive into the chart in a very structured manner. So by using the arrow keys, you can move down one level of abstraction to look at, the x-axis, the y-axis, so on and so forth. They use the arrow again to move into particular intervals or categories or data points and so forth. And also other sorts of navigational structures to be able to move around the visualization in a spatial manner. So let's look at Jonathan actually using this hierarchical structure.
So here I have a demo of a scatter plot of penguin data. And to a screen reader, our system represents this scatter plot as a keyboard navigable data structure that contains text descriptions at varying levels of detail. So when a screen reader user first encounters this visualization on a page, they'll be able to read off a high-level alt text description of what the chart is. So
a scatter plot showing body mass and flipper lengths of penguins.
And if they're interested in getting more detail about this visualization, they can dive in by pressing the down arrow key to descend one level in the hierarchy and access descriptions about the different encodings of the scatter plot. So I'm going to press the down arrow key.
X-axis titled flipper length, mm for linear scale with values from 170 to 240.
I can press the left and right arrow keys to flip through descriptions of the other axes and legends.
Y-axis titled body mass G for linear scale with values from 2,500 to 6,500. Legends titled species for color with 3 values, Adelaide, Genstrap, Gen2. Grid view of scatter plot.
Cool, so let's say I am interested in getting more information about the x-axis. I can use the left arrow key to navigate back to the x-axis description and then press down one more time to descend a level of detail into the x-axis.
Legends titled, y-axis titled, x-axis titled, flipper length, mm for the range, 220, 230, 35 data values in the interval.
So on this level underneath the x-axis, I'm accessing descriptions of intervals along the x-axis, and it's reading out to me how many data values are contained within each interval. So by pressing left and right, I can kind of get a sense of the distribution of data along the x-axis.
Range, 200, range, 190, range, 170, range, 190, 200, 113 data values in the interval.
So let's say I am interested in this range from 190 to 200. I can then press down arrow again to dive into the individual data points that are contained within this interval.
1 of 113, flipper length, mm, 190, body mass, G, 3,650, species, Adelaide. 2 of 113, flip 3 of 113, 4 of 113, 5 of 113.
So let's say that instead of moving up and down this hierarchical structure, I would rather just move around the XY grid in the scatter plot, as if I were kind of feeling around a tactile graphic, for example. I can start by navigating over to the grid view of the scatter plot.
Y-axis type legends titled grid view of scatter plot. 79 data values in the interval, body mass.
And once I descend into this part of the hierarchy, I can use the WASD keys to move up and down different squares along the grid.
10 data values in the interval, body map, 25 data values in the interval, body, 32 data values in the interval, 0 data, 3 data values, 23 data, 30 data values in the interval, 3 data values in the interval, body mass, G.
And so similarly to before, it's starting off by giving me the number of data values that are contained in that square so that I can get a sense of the distribution of the data.
And so we actually developed this structure through a co-design process with a blind collaborator of ours, Daniel Hodges. And Daniel mentioned that this was actually the first time that he felt like he was building a mental representation of what a scatter plot was conveying. And the reason was that it wasn't just the overview first, details on demand, right? The hierarchical structure, but we gave that sort of spatial navigation, affordance as well. And so, this work has been open sourced to this library called Ollie that we're continuing to develop. But I wanted to return to that notion of articulatory distance, because what we were seeing is that, we're not changing the semantics at all, right? The semantics are pretty poor. All we're talking about is so many data values, this range, this axis, right? We'll come to semantic distance in a bit. All we were manipulating was the articulatory distance, and that had a massive impact on participants' mental models. So, in our user studies, someone told us, it's giving me a different way of thinking because I know how to drill up and down and get different layers of data grids for an overall picture. And I'm thinking more in terms of spatial terms than I was before. I'm thinking about moving through a grid and drilling down information into that square to get more information. And really, this is, for us, just the tip of what I call this articulatory iceberg. There's a lot of seemingly even low-level things that really, really matter, such as the order these tokens are read out, the verbosity of these tokens, and in particular, also going back to this idea of a mental model, what people think is actually happening as they sort of descend into the hierarchy. So depending on the visualizations, as people navigated the structure, what they told us they felt like they were doing was just reading the visualization, right? Moving their focus around. But for other visualization forms, the same hierarchical structure, the same navigational opportunities, they now said that it felt like it was zooming into the data instead, right? And zooming in the visualization literature is something we traditionally think of as an interactive operation, not a static reading operation. Right, so there's some interesting blurring happening between notions of static reading and interactive manipulation because we've manipulated that articulatory distance. But in all of this, like what are we doing with the semantics? Like it was pretty poor, right? And this is where I think large language models and ML models are going to be pretty central. Right, and allowing us to cross semantic distances at a scale, and a level of granularity that we would not be able to do before. But before, we can actually do any of this, we have to deal with the fact that, the critique I levied at the start was that these LLMs have a latent learned representation. They don't have explicit domain semantics. And so what we need to do, I think, is actually start by imposing a conceptual model on these generative models, right? So what does it mean to produce a good textual description of a visualization? That's essentially the question we're trying to grapple with. And so in some work that my then PhD student at the time, Alan Lundgaard led, we crowdsourced from cited readers, over 2,000 captions of visualizations, and led a sort of a very involved qualitative grounded theory process to identify basically 4 kinds of semantic content that we would want to be able to express. The first is just the chart construction properties, right? The encodings, the titles, things like that. One level higher up are sort of statistical properties, like Google has the greatest price over time. One level higher up than that is, the perceptual and cognitive things that we tend to say is where the value of visualization lies, right? Identifying and articulating complex trends and patterns like a gradual stair-shaped rise between 2005 and 2006. And then finally is the sort of, contextual domain-specific, pieces that we often associate with, say, narrative, narration or journalistic annotation or things like that. And it was really important for us to do this more formative work of figuring out what the conceptual model of textual description should be, because, if you'd asked me ahead of time what my expectations would have been, I would have thought like, oh, we all want the textual descriptions that are, doing the narration, the contextualization, explaining the trends and so forth, right? I'm seeing a lot of nods. Turns out when we asked sighted and blind people, their preferences were really, really distinct, right? So sighted readers, because our visual perception is doing so much work, we don't get a lot of value out of levels 1 and 2 because we're getting that visually. But for blind readers, it's that quote again from before, right? Blind readers wanted time and space to do the perception and interpretation tasks themselves. So if they had a textual description that was, doing that work for them, level 4, they rated those least useful because they felt like their agency was being robbed from them. And so now that we have this, conceptual model and we better understand some of these sort of highly individualistic user preferences, that's another reason that we might want an ML intervention, is because we can, imagine all the ways in which someone might want to customize a textual description, or how a textual description might vary for different tasks in different contexts. But as a first pass, what we are going to be doing next month is releasing a data set of about 12,000 pairs of charts and captions. The captions include a generated L1 caption that includes all the sort of, elemental construction details following best practices for accessibility. And then we've crowdsourced really high quality L2 and L3 captions that express some of the, perceptual cognitive features. But what's interesting here is that there's still some semantic distance left across, because we've, defined a conceptual model of the textual descriptions, but we need to figure out how do we convey the semantics of the chart itself to the model, right? And there's lots of ways in which one can capture chart semantics. You might just give the model an image of the chart, right? The raw pixels. You might give it the data table. You might give it the SVG, right? And a priori, I thought that the SVG would probably be a good balance between capturing some of the perceptual features of the image and some of the kind of computational features of the data table. Turns out, and in retrospect, this makes sense, the data table does just fine, right? It's trivial for the model to learn the mapping between the data table and the scene graph. And yet, in the models that we've trained, and we've done some early experiments with GPT-4, the captions are not that good. They're reasonable. They're about 50% accurate. So there's still lots of work to do. I'm not sure the work to do is actually on the caption collection part. I think it's on the definition of chart semantics and figuring out how do you represent, those semantics to a model. We're very used to thinking about, designing representations for people, right? That's what programming language design is. But I think there's some really cool opportunities to think about what it means to impose a conceptual model on machine learning models and what it means to represent, concepts to them. So that is sort of, one thread of work that we're working through. And this is really about imposing a conceptual model, but there's also a way of thinking about bridging that semantic distance by aligning conceptual models instead, because one could argue that what predictive machine learning models are doing is actually learning a representation of their domain, right? And that's why you get fields like explainability and interpretability. Here's a very common technique called a saliency map, where the idea is that, the pixels that are most lit up are the pixels that are most contributing to, the classification of this image as a toy terrier. Now, if I look at these visualizations, I can feel like they're really telling us something, right? And a lot of people have got a lot of value out of these saliency methods. But I would argue that if we think about it through the lens of direct manipulation, and particularly that gulf of evaluation, we are the ones doing the perceptive and interpretive tasks to cross that gulf, right? There's nothing, this is just a random array of white and black pixels. I am the one that goes, oh, actually, that set of pixels looks like a dog snout. That set of pixels looks like spots on the dog, right? Why isn't the saliency map or the model actually helping me through that semantic sense-making task? And so this is something my PhD student, Angie Bogus, has been working on with some collaborators at IBM Research with a project that we call Shared Interest. And the idea is that, at a very crude level, can we just kind of compare, very similar to sort of ideas of precision and recall, the set of features that turn up in a saliency, right? So the individual pixels, and compare that to the set of ground truth features that someone might have annotated in terms of, say, a bounding box on the image. And if I've got this comparison, there's lots of different sorts of coverages that I could calculate. For instance, I could calculate a ground truth coverage, right, which is about how strictly the model relies on all the ground truth features. And it's sort of analogous to something like recall, right? It's a proportion of ground truth covered by the explanation. And if we do that, so here in this case, the bounding boxes are human annotation, the orange are, the saliency features, and then you can see the outcome predictions. In gray, that's the what it should be. And then, on the right is what the model outputted, and we're using red or green to indicate a incorrect or correct prediction. We can see that, if we compare sort of, these high coverage features where the model made a correct prediction, we'll see that actually there's a lot of overlap between, the saliency features and the ground truth features, right? So a lot of high ground truth coverage. On the other hand, if you've got high coverage but an incorrect prediction, you're seeing sort of a distraction happening here. So it thinks this is a laptop, even though it should be a chihuahua, and it's got that sort of broader context of the image that it's taking into account. Another type of coverage we might measure is actually something called saliency coverage, which is how strictly the model relies only on the ground truth features. And this is kind of analogous to precision. So for instance, high saliency coverage with correctly classified inputs, is where a subset of the object was basically sufficient to make a prediction. Whereas, high coverage with an incorrect prediction was where the model was actually kind of overfitting, right? It was using this tiny part of the overall image and then sort of rapidly arriving at an incorrect conclusion. And then finally, sort of the third sort of coverage would be just IOU, right? So the intersection over the union. And so what's interesting about shared interest is that it gives us a way to start bridging that semantic distance, but this time by aligning the conceptual, that latent model that the model has learned, and our own conceptual models. And what's interesting is that those patterns sort of repeatedly emerge across a variety of different modalities, a variety of different models. We gave those patterns names like human aligned or confuser or context dependent. And now that we've been able to sort of bring that meaning to, saliency methods, we can explore different articulations. So here is sort of a somewhat traditional visual analytics interface. And you can sort of, go about, tweak the drop downs, use the individual sort of metrics in terms of, coverage distributions or IOUs to sort of brush and filter. And then those recurring patterns are captured as cases, on the left-hand side. And we tested this tool out with a board-certified dermatologist. And they made a really interesting sort of observation when they looked at these context-dependent cases. In particular, as they picked that pattern, and they were looking through, these images, they sort of had this realization of like, wait, is there something to learn from what the model is doing here, right? They wondered if the model is seeing something we don't truly appreciate in the clinical image, because they agreed with the way the model was making the decision. But as they compared the human annotated region with the model region, those overlaps and parts that didn't overlap, they were like, wait, what's going on here? Like, is there something for me as a board certified dermatologist to learn in terms of how I should be doing, skin lesion detection? But this isn't the only articulation we might want. Here is a more fun interface where I could just interactively specify ground truth by brushing. So I could brush on, the person's hat. And this is a very traditional ImageNet model that was only trained on dog classes in ImageNet. So that means that it's actually being penalized for, all these other class definitions. And yet we're noticing that it's learning those representations nevertheless, right? So when I brush on the hand, I see that, it is detecting images classified as printers or hens or things like that. And the reason is because I'm using shared interest as basically a query into the latent space to figure out what's going on, right? So it's almost a way of doing what if analysis or counterfactual reasoning or things like that. And it also allows us or hints at the possibility of asking new kinds of questions of the model. For instance, I might ask, what is the essence of a dog, right? By starting by brushing the entire dog and going, okay, great, I get a bunch of labels out that are, different breeds of dogs. And then I could start to selectively brush smaller and smaller regions of the dog. In this case, I'm just brushing its head. Yep, Basset Hound, Afghan Hound, Labrador Retriever. To find that actually, I just need to brush on the dog's nose for the model to still correctly classify that this is a dog. Right. And I think there's something interesting here, right? I don't want myself or us to be overfitting to say that, we should be reclassifying our biological taxonomies to be on nose shapes and nose characteristics, right? But there's nevertheless maybe something interesting for us to learn about why is it? Like, is there something really that distinctive about noses that, the model is able to make that high level of a fidelity decision just based off of that? And so at my most speculative, and I'm going to put large like caution tape banners around the next couple of minutes of this talk by saying that, you know, we've thought about these models so far purely as tools to help us bridge existing semantic and articulatory distances. And I wonder if there's an opportunity to use the models to actually discover new conceptual models, right? To actually do the work of science. And, you know, whereas imposing the models I liken to generative models, aligning I liken to predictive models, I wonder if there's space for something that I'm, you know, gesturing at that I think is abstraction models, right? Models where I don't actually care about their output at all. I don't care that they're producing something. I don't care that they're making a prediction about something. What I care about is what abstractions are they learning, right? How are they choosing to model the world, and what can we learn from them about the way that they're modeling the world? Now, the reason I want to erect a lot of caution tape around this is not just because I'm not an ML person, this could be total bullshit, but because I think there is an epistemological risk here, right? The risk here is that, you know, just like we're seeing through natural language, people are starting to anthropomorphize the models. There's a risk with this, you know, this third direction where we start to treat the models as ground truth, right? And I think we need to be very careful and thoughtful about what it is we're doing and what it is the models are doing, who is doing the sense making and the semantic, discovery, who is doing the perception, who is doing the interpretation. But I think there is an opportunity to conceive of these models kind of in the way we do microscopes and telescopes and things like that, right? And allowing us to look at the world through a different lens, a lens that potentially mirrors the way that we do a lot of our work. Certainly, if I think about how do I design programming languages like Vega Lite, what we often do is go look at a lot of example visualizations and then try to distill recurring patterns, right? Capture them in abstractions. It's not altogether different from what a model is doing, but a model is doing it at such a scale and in a sort of, you know, with a different set of quote unquote values. I'm not sure that's the right term, but it's optimizing for a different set of concerns than we do when we're designing a programming language. When we design a programming language or any kind of user interface, we're designing for people, hopefully, usually, right? And we're designing for the affordances people have in terms of perception and cognition, right? One of my favorite heuristic frameworks for evaluating interfaces is the cognitive dimensions of notation, right? The connection back to Doug Engelbart there. And one of the properties of the cognitive dimensions of notation is this idea of viscosity. How difficult does the user interface make it for you to move from one expression in the user interface to another? It's not clear that machine learned models care about cognitive principles like viscosity at all, right? And maybe that's okay, because maybe there's an opportunity to learn something by trading off the affordances we have typically prioritized. Maybe there's some opportunity there for us. And so with that, I am happy to take questions.